So, good day, everyone. I'm on behalf of our small development team. I'm here to present a research GPU compiler project called KernelGen. So far, modern GPU computing already exists for some 5 or 6 years, and out of this time, most of this period of time, only 2 major GPU programming technologies were CUDA and OpenCL. If you ever tried to port existing large application with originally intended for CPU onto GPU-enabled cluster, you might already know that it would involve a lot of at least a significant code modification. Fortunately, recently situation started to change because different compiler groups started to look how it would it be possible to conserve the original source code representation and take and perform the GPU code generation automatically and take it behind the scenes. So one most famous technology of this kind is currently Open ACC. Open ACC stands for a set of directives or annotations to existing high-level programming languages like C and Fortran. And it allows a developer to manually insert annotations on existing source code that will guide the compiler, that will point out for compiler the regions of code to be taken onto GPU. And this internally for compiler, these directives are working as hints to perform automatic analysis of computational loops and perform GPU code generation underneath. OpenACC is a good step forward, but unfortunately it has a lot of limitations, and I will show you some examples. Also, OpenACC is a little bit conservative about the role of GPUs. It considers the GPU only as a passive accelerator that is as an extension to the computational unit that may very likely change in near future. So the main goal of KernelGen project is to make another step forward, try to relax OpenACC limitations, introduce new features, and make it even more robust, more usable for large numerical applications. Okay, so since this presentation is mostly intended for potential users, let's now jump directly to practical examples. So in this case, we have simple program in Fortran, which is generating some data and performing some trigonometry in 3D loop here. So if you would have this program in Linux, you would probably compile it with gfortran, like the most accessible free compiler. In case of KernelGen, you can use the same options because we are fully compatible with GCC, but just change the name of the compiler. Instead of gfortran, just use KernelGen gfortran. It will also generate standard ELF binary, but that will be a hybrid binary because if you execute it as usual, binary file name and arguments, it will be executed on CPU. But if you want to execute the same application on GPU, you need to do the same thing, just add the additional environment variable. And you'll have some impressive speed up. So same code in C, same magic for compilation and deployment, and same speed up. Okay, so these are the most simple examples where we can deploy our compiler and have GPU code generated automatically without any CUDA or much GPU knowledge. So OpenACC, although it's currently supported by multiple vendors, it currently has some serious limitations. Many of them are listed here: external calls and pointers analysis. Let's consider each one by example. So by external calls, I mean the ability of compiler to generate GPU code from loops, which are essentially the same loops as seen in simple examples, but with calls to external functions, which are defined in different compilation unit. In case of OpenACC compiler, PGI OpenACC compiler specifically, you will have a restriction. Function procedure calls are not supported. This happens because in case of PGI, all GPU code is considered self-sufficient on compile unit basis, which means you need all the dependencies of your GPU code to reside the same compilation unit, the one you're currently compiling. In case of KernelGen, we are taking the dependency resolution step to linking, which means on linking step we have access to all objects the final binary will be combined from, and all GPU code dependencies could be easily linked at this step. So it's not really hard to do. So in this case, KernelGen can parallelize this loop, while OpenACC can't. The same situation is in case of static libraries. Since we need to support particular applications that consist of multiple static libraries, we had to add support also for linking dependencies from static libraries, which is also a very useful feature for large applications. Pointers tracking. So pointers tracking, or sometimes in compiler theory referred as alias analysis, is a problem of tracking down the origin of pointers. Let's consider this simple function. So here we have 3 pointers. Each pointer is standing for input or output array used in the computational loop. So from the compiler point of view, it's on compile time, it's very hard to determine if these pointers are referring to the intersecting memory ranges, or if they are referring to independent memory ranges. So in most of the cases, users probably assume that these pointers are independent. But compiler have to be reliable. He must know for sure. And for this reason, in case of OpenACC compiler, you will have also some nice messages. And this loop, although it is parallel, it will not be taken on GPU without additional hints. You can certainly add here loop independent and things like that. In case of KernelGen, we are doing a little bit of JIT compiling, and we are taking the final analysis point and the final decision making about GPU parallelism into runtime, which means we can additionally utilize the information from the runtime context. Specifically, we can substitute the exact values of pointers and exact values of loops dimensions, and just compare the memory ranges in numbers, and have the reliable decision about the parallelism of the entire loop case. So here we have the static control part representation for aforementioned loop, And here is the read-write access analysis after substituting pointers and constants. And this technique helps us to figure out the loop is actually parallel and could be automatically taken on GPU. Okay, so besides relaxing OpenACC limitations, we also tried to address some language-specific features that may be used or not used depending on the developer coding style, but in any case are very nice to have. So here I will show examples for handling different forms of loops, parallelization of implicit loops, and parallelization of loops with pointer arithmetics. Since we are using LLVM-IR, from our point of view, every loop is lowered into some intermediate representation, which is actually quite low level. We don't see loops of different kinds. We rather see the representation like assembly language, like loop header, loop body, phenode, induction variable, and backedge. And it may happen that even a while loop would suit the pattern in the low-level representation that we are looking for, because we need to resurrect, we need to get back the loop idiom from this intermediate representation. So in this case, we have a do while not arithmetic do, but still, since it's based on arithmetic, it could be parallelized, and it's recognized in the same way as arithmetic do loop. And OpenACC allows only for or do's. Parallelizing of array-wise code. Array-wise code means that in Fortran, developers may use compact form for specifying collective operations on arrays. So here, Z, C1, and C2 are complex numbers arrays of single dimension. And this statement means that we apply the conjugation and multiplication to each corresponding element of each array. Also, the good thing about our technology is that front end is expanding the statement into plain loop. So again, from our internal representation, this statement is converted into plain loop. And it also could be parallelized like in first two easy cases. Pointer arithmetics. LLVM-IR is low level. And from our low-level view, it doesn't matter if we had original array accesses by indexing or array accesses by pointers. From LLVM-IR, everything will be accesses from pointers. For this reason, we can parallelize these kinds of loops if developers prefer to make accesses through pointers and increment pointers after each iterations. So in case of OpenACC, this is completely restricted. Well, honestly, I don't have an idea why they are so restrictive, because in our case, we're also able to parallelize this language feature, this code styling. Okay, so hopefully I convinced you we have some nice language features. Now, what about performance? So specifically for our compiler toolchain, we designed benchmarking suite, which contains 14 different test cases with different compute kernels, but all they follow the same general algorithm, which resembles the explicit in time numerical solver. We decide that to make sure we can easily address the majority of computational code in scientific domains. So what happens here, we have outer time iterations, which are not parallel, and inner spatial iterations, which are the stack of nested, 2 or 3 nested loops iterating through each grid point in a regular compute grid. And the same source code is adopted for OpenACC, for Mike, and for KernelGen. So in case of KernelGen, we just ignore all directives. In case of OpenACC and Mike, we add additional directives here to allocate input-output data buffers and copy input data slices from host to GPU. During time iterations, we are not offloading any time slices back into the host memory. All computations are performed in GPU memory with swapping of time levels. And after we have the final slice, only the final slice is offloaded to host and checked for results correctness. Okay, so this is the performance chart. Let me explain what these columns means. So here is the one level. You see, one level means that the column with height of 1 denotes KernelGen performance is the same as PGI OpenACC performance. We have newest KernelGen revision here and newest PGI OpenACC compiler. Where columns are below the 1 level, that means KernelGen is slower than PGI. Where we have columns higher than 1, that means they speed up against PGI. So it turns that open source technology can sometimes outperform the commercial solution, and I will try to present you some performance factors which we try to analyze to track down the origin of performance differences. So please note that we have performance degradation in comparison to PGI for 3 tests here: matmul, matrix multiplication, matrix vector, and sun cosine. And almost all other cases we perform better than PGI. The same chart for double precision, so they are almost the same kind. Also a group of three tests are a little bit worse than others. Performance factors. So first of all, we can make a free of charge performance improvement because it turns OpenACC is not doing anything about cache configuration. Current OpenACC compilers mostly do not utilize shared memory. In KernelGen, we are also not able to utilize shared memory for caching at this point. So it would be logical to prefer a larger L1 cache. So using just this only line, you would have some performance gain against PGI for free. And probably PGI guys would also decide to make this call for every function they are generating for OpenACC if they're not using shared memory. This is the easiest one. We have different compute grids. So we made a survey, a complex testing of best block sizes, and discovered that this block size is the best one. Although we previously used also this block size and also had some performance gain, but it was much it was much less performance gain. And another difference is we are using 3D compute grid, and PGI is using 2D compute grid. So probably they have more branching in their kernels because they need, in any case, they would need to keep additional loop right inside the kernel code. Okay, these are good things. So let's now discuss not so good things. So here is the LLVM for MATVEC, and the key property of MATVEC and matrix multiplication as they are implemented in our test suite is that they are using reduction. Reduction means you have an accumulating variable which receives contribution from every iteration of some kind of loop. So here is this loop, the header, the footer, the body, and the go-to condition in intermediate representation. And our problem is that in LLVM, by some reason, we have reduction under-optimized. It's improperly optimized because here we have stores to the accumulating variable inside every reduction loop iteration, which is very inefficient because you would rather need to have an accumulator on register, accumulate all factors from all iterations, and only afterwards perform one store of final value into global memory. So it turns that this is the reason for us to have MATMUL and MATVEC to be slightly slower than PGI. But with LAS analysis, I think it could be improved. Code generation. So for PGI is actually a source-to-source compiler because they are doing their own front end. Then they are doing their own optimizations, but they are not generating PTX code directly. They rather generate C code, very ugly C code, which is resembling assembly or intermediate representation. And this C code is then chained to standard CUDA compiler and VCC, and only VCC generates the PTX code. In case of KernelGen, thanks to open sourcing NVPTX backend to LLVM, we have a seamless pipeline because we lower GCC intermediate representation to LLVM, then optimize and analyze code in LLVM representation, and NVPTX backend generates PTX code for us right from the LLVM IR. Just for reference, we also have performance charts against CPU, but they are not so important, I believe, so just some big numbers against CPU version in single core, just for reference, that we are doing something, we have some correct numbers. But I believe it makes more sense to compare KernelGen to tools like Open ACC to make up a reasonable intercomparison of the technologies of the same kind. Please note that we are not using any kind of directives at this moment. So users can supply us both parallel and non-parallel loops. Like in this case, we have inner loop as reduction. We currently don't support parallelism of reduction. So in this case, this loop will be serial. But outer loop contains independent iterations. So in case of our outer loop, we will generate the GPU compute grid, and each thread inside GPU kernel will have a loop with reduction. So the entire loop will be taken on GPU. One of essential design point behind KernelGen is the target to coexist with MPI level of parallelism. So we decided to cook our compile to change and execution pipeline in such a way that CPU MPI node could be easily transformed into GPU MPI node. How it happens in this case. So this chart is from this program, but from MPI version of this program with matched filtering distributed against multiple MPI nodes. And what happens here is the blue line is scaling for up to 12 CPU cores, and MPI node corresponds to CPU core. And here, MPI node corresponds to one GPU. And additional resource of parallelism is added by KernelGen compiler into each MPI node. We are not making any changes to code. Only CUDA visible devices environmental variable setting for every MPI node in order to specify appropriate GPU for each MPI node. Okay, so in case of commercial OpenACC compiler, you will need to pay somewhat about $1,500 for a single license. In case of KernelGen, you don't need to pay anything because all the components we are using are freeware, and most of them are open source. So here, GCC and Dragon Egg are used together to convert high-level languages like C and Fortran using GCC front-end into LLVM representation. LLVM optimization passes, polyhedral analysis for LLVM, and also our own runtime component are performing analysis and specialized LLVM IR code generation for GPUs. Once we decided the loop is appropriate for GPUs, we chain the IR to NVPTX backend, and PTX backend generates the PTX code for us, and then PTX goes to the standard NVIDIA stack. And also we have some open source tweaks in the hardware assembler. But this is a little bit different story. Some words about compiler pipeline. So again, we are a full compiler, not source-to-source compiler. For this reason, we have all stages in complete state: compile time, link time, and runtime. One significant difference with the regular compilers is that we are taking the final analysis and optimization and code generation step into runtime in the place where we actually approached the code line where we have a loop that might be appropriate for GPU acceleration. So we are taking part, we are working mostly like a JIT compiler, we are taking parts into the runtime. Another unusual thing about KernelGen is the way how we is the so-called GPU-directed execution. This means that we are trying to make GPU as self-aware as it's possible. So it's try to track all activities like host calls, like requests for compiling and analyzing and compiling loops. All data initially resides GPU memory, and there is a so-called main kernel, which is one-thread kernel, and it doesn't affect the overall application performance, but it's alive on GPU during the whole application lifetime, and manage the state and control flow of data and code on GPU. The origin behind this decision are some benefits or potential benefits for future. For instance, For instance, we have no need to manage host device memory transfers and track hidden data dependencies. Also, we favor we favor the code with a large amount of potentially parallel code because all our data is initially on GPU. It would be easier to keep it there. It would be possible to run long uninterrupted kernels if we are using GPU with dynamic parallelism feature. So main kernel will be just spawning other loops kernels from itself using dynamic parallelism without making any callbacks, without utilizing CPUs. The CPU will be just free. You can use CPU just yet another compute node if it's appropriate for your application. Actually, the main reason we decided so is transparent transition of CPI MP nodes into GPU MPI nodes. So previously, what we had on CPU is mostly taken on GPU, with exception of non-portable codes where we don't have source code available, with exception of system call libraries and inefficient loops that are inefficient on GPU. Everything else is just on GPU, like if the GPU is the main device in the system. That will be probably true in very near future. Yeah, and in case of regular CUDA or OpenACC compilation, all kernel code dependencies like math functions will be taken together with every kernel where they are used. So by default, the scheme will have a lot of duplicates of the same code. In this scheme, we are trying to reuse device function and any kind of common code that may happen, that may be shared between multiple kernels on GPU. Okay, so now if we will take if we will rotate this scheme by 90 degrees, every application in case of KernelGen starts with some kind of version switch. Then we compile the main kernel and launch it on GPU. And once we need something, once we need a host call or call to another GPU kernel, we make a callback to host, and host performs loop kernel analysis, using additional runtime information, and JIT compiles and launches it. The final kernel is launched into the parallel stream, and the GPU data is naturally shared between stream 1 and stream 2. It's shareable here. So after loop kernel is finished, we also have a callback. And after the callback, we resume back the main kernel. And during this period of time, the main kernel was in busy state. It was suspended, but it was still alive on the GPU. Yeah. This is the case of loop kernel. Another case would be if we have a need to make a host function launch. So host function would be system call from external library we don't have source code for, or a call to loop, which is inefficient for GPUs. So in this case, we'll have same JIT compile pipeline and libffi foreign function call for launching host function. In this case, GPU data will be lazily mapped to host from GPU by request as needed, using the page fault handler. And once the host function is finished, we will reload back the dirty memory pages host function might update. We'll write them back to the GPU memory. And the same way, resume main kernel execution. So there could be multiple host functions or loop functions calls. So this is the general scheme like what we have for execution workflow in KernelGen. The key things about the loop analysis pipeline. So we rely on polyhedral analysis passes contributed to the mainline LLVM. But as you may know, polyhedral analysis is also capable to transform serial loops into parallel loops. We are not using this functionality at this moment. We are utilizing polyhedral passes only to make sure the initial representation of loop contains independent iterations. But we combine these polyhedral optimization passes with substitution of global variables and pointers and integer parameters like loops dimensions, which allows us to make more reliable guesses about iterations dependencies. And another our contribution is the mapping of final loop, in case it's parallel, onto GPU compute grid. So we had an original LLVM IR. In case it's parallel, we are specializing this LLVM IR further into GPU-enabled, GPU-tuned IR, and code-gen it to PTX using NVPTX backend. Let's briefly walk through KernelGen code generation steps. This is the simple function. This is the Gimple form. The Gimple is used as intermediate representation by GCC. We are not using Gimple, but we use DragonEgg to convert Gimple further into LLVM-IR. So this is the equivalent representation of Gimple created by DragonEgg. And the IR here describes the entire function from as it was originally in the application source code. So at the compile time, we are trying to guess what loops would be potentially capable for GPU execution. Note, at compile time, we don't generate the final GPU code because we don't have enough information for many cases. We are only trying to extract loops just to make some preliminary representation for loops for further analysis. So in this case, we have an extracted loop here, and we have substituted values for pointers and for dimensions here. And it's a little bit slow, right? And in case the loop is parallel, we specialize the intermediate representation further for GPU code generation. As Jan mentioned, there are special GPU-aware intrinsics contributed in LLVM. Like in this case, we have the intrinsics for reading the GPU compute grid from kernel. PTX kernel stands for kernel function. PTX device stands for device function. And finally, from this LLVMR, we generate PTX by means of NVPTX backend. And PTXS finally generates the hardware assembler for us. Okay, so although we currently have a pretty functional prototype, there are some important features still not covered. Currently, we support only simple loops indexing. We don't support arbitrary indirect indexing, which is believed to be a very useful feature for sparse linear algebra or structured unstructured grid. We currently do not support reduction at IDEOM. However, it's currently supported by OpenACC. Yeah, and we may face some complications with code generation just because it's prototype, it's preliminary version. But still, KernelGen project implemented a full compiler prototype that can produce GPU kernels for unmodified existing source codes. We paid a lot of attention to have a good level of C and Fortran languages support. As benchmark suit showed, we have some interesting performance gains against commercial compilers, and this comes for free. And KernelGen tries to relax current OpenACC limitations and introduce some nice features. And we try to design our pipeline with existing MPI applications in mind. And finally, KernelGen is based on freeware and mostly open source technologies. Although it's prototype, it's currently ready for testing. So if you would like to test, please welcome. You'll need a fairly modern GPU, Fermi or Kepler. You will need recent CUDA driver and a bit of patience to follow the installation, build the installation guide. Once you installed, you can source the virtual root of compiler, and you will have all the compilers for Fortran, GCC, and others available from the command line, and you can just test the code for arithmetic GPU code generation. In case if you see some problems, just use our public bug tracker. We are currently also studying COSMO and WRF, two major numerical value prediction models. So although this work is currently not complete to the final point, you can already compile these codes using KernelGen and even run them to some extent. What you need to do is to populate a WRF configuration file with 3 or 4 new configurations, copy-pasted from Fortran, and just use KernelGen Fortran and deploy the final executable with KernelGen run mode environment variable. Same thing in case of COSMO. In case of COSMO, if you are using Open API for MPI implementation, you can use these environment variables to reconfigure Open API to use KernelGen compilers as underlying compilers and compile the COSMO source code. And also you can deploy it as usual. Not too much magic. And the main reason to give this presentation on GTC is that we will try our best to make this to develop this project further. And in order to do so, we need more partners, we need more contributors and users. For instance, if you have your code available for GPU, available for CPU cluster, we can help you to try it on KernelGen and deploy on some of HPC, high-performance clustering facilities. We also have our own small compute nodes, and you may try to evaluate there. We also welcome contributors with compiler technology skills. There are a lot of open submissions like tiling, sparse data algorithms, and many more. And we also welcome new proposals related to KernelGen, LLVM, Poly, and other technologies. And even if you have a different view of GPU compiler perspective, but KernelGen can be reused for you as a framework, as a tool, we are also ready to help and address your needs. By the way, it might be possible to make yet another OpenACC compiler based on KernelGen technologies, because we have most of them underneath. So this is the download link for this presentation. And if you have some discussions or questions, please don't hesitate to contact us in our mailing list. And thank you for your attention.